Assalamu alaikum. Now let us focus on motion in or 2 and 3 dimensions, but the simplest case when you have constant acceleration. As we have done before in motion in 1 dimension. So now we'll talk about motion in 2 and 3 dimension, but with a special case of constant acceleration. I think by now you are familiar with motion in 1 dimension with constant acceleration. If you remember this from previous discussions, in 1 dimension we had 5 equations of motion, and these equations, if you remember, V final equals V initial plus A multiplied by time t. The second equation was delta x equals V initial t plus 1/2 A t square. Third equation was V final square minus V initial square equals 2A delta x. Fourth equation, where the acceleration is missing, delta x equals V initial plus V final divided by 2, all multiplied with time. The last equation is similar to the second, which is delta x V final t minus 1/2 A t square. Let us try to see how do we treat with motion in 2 and 3 dimensions when the acceleration is constant. We'll use the same equations, but we have to notice these changes in 2 and 3 dimensions. These equations will look like the following. Equation number 1. Here, the velocity was in 1 dimension. Okay, so it was either in the positive x or in the negative x. But now it will be vector. So V final as a vector will be V initial as a vector plus the acceleration as a vector multiplied by time. So this velocity, final velocity, might have x component, y component, z component. Similarly, the initial velocity will have these components, all of them, or maybe 1 or 2 of them, depending on the problem. And the acceleration also might have 3 components, 2 components, or 1 component, depending on the problem. The nice thing here that we can write this equation into 3 components. The first component will be V final x equals V initial x plus AX t. So we'll treat the velocity along the x-axis alone, separately from the the y component of the velocity. So I can write it here, the other component, V final y equals V initial y plus AY t. Okay, the third component, if you can correctly guess, it will be V final z. So this is the z component of the velocity, will be the initial velocity along the z plus the acceleration along the z-axis multiplied by time. So nothing new here, but rather than dealing with a single equation in 1 dimension, now we can have 3 equations or 3 components of the same equation, equation number 1, equations of motion. Let me give you one more example, which is the second equation. Second equation here says delta x, now I write it as delta r, okay, equals, here V initial, I write it, but now as a vector, okay, time plus 1/2. The acceleration here will be a vector, and now this is the time square. This equation has 3 components. The first one, I can write it as delta x, okay, equals v initial x multiplied by time plus 1/2 ax t square. The second component along the y axis, and this can be written as delta y, will be v initial y t plus 1/2 ay t square. And the third component, I can write it as follows. This is the third component, which is delta z equals v initial z multiplied by time plus 1/2 az t square. And we can say the same for equation number 3, equation number 4, and equation number 5. We have to notice one thing here, that the time is the common physical quantity in all 3 components of each equation. This is very important rule, and we have to highlight it here. So notice that the time is the common physical quantity in all components of the equations. Okay, if you are talking about the x component, the y component, or the z component, the time is common in all of the 3 components of the equations. This will be clear in the example when we solve an example shortly, inshallah.